Right, good morning. Welcome to your second lesson of your organic chemistry unit of work. You should have your organic chemistry booklet in front of you, and if you turn to page 10 in it, you will see that there is a knowledge check that outlines just some of the ideas that you will have covered in lesson 1. If you could pause the video now and spend a few minutes looking back over lesson 1, having a go at that content, and just seeing if you can do it, then unpause the video and we'll go through the answers. Right, hopefully you've had a go at that and you've unpaused the video. So if we just go through the answers nice and quickly, where is crude oil found? So in rocks or underground would be the appropriate answer. Name the first 4 alkanes. You've got methane, ethane, propane, and butane. Why are alkanes saturated? We call them saturated because they use all of the 4 bonds in a carbon atom to covalently bond with other atoms. Now a little bit of a recap from previous unit, not related to this, but it's good to recall content. What the 4 components needed for photosynthesis: have light, warmth, water, and CO2, carbon dioxide. State the number of bonds a hydrogen atom can form. That is just 1. Give the name of these types of bonds. Mentioned it already. Covalent bonds. What's the general formula for an alkane? So if you have the number of carbon atoms in an alkane, Cn, you would then be able to find the number of hydrogen by doubling it and adding 2. So we'd write it as Cn equals H2n plus 2. Name the 2 elements that make up hydrocarbons. You would call those carbon and hydrogen. Good. So if we move on to the next page. So if we just review the content a little bit from last lesson, read through lines 45 to 53 together. So hydrocarbons are molecules that are made up from hydrogen and carbon. So they're molecules, which means the hydrogen and the carbon are chemically bonded. Make sure you add in that annotation for me. The atoms are bonded covalently by sharing pairs of electrons. So remember, that's the definition of a covalent bond, where they share electrons, and covalent bonds are between non-metals, like these 2. So they're between non-metals and they share pairs of electrons, which makes the bonds strong. Carbon can form 4 single covalent bonds, whereas hydrogen can only form 1 single covalent bond. And if it is a single covalent bond, it means the atoms between themselves share 1 pair of electrons. Okay? The structure of the carbon atom allows it to form families of molecules, particularly rings and chains. So you would say that these are shapes of molecules. And shapes of the molecules are important. Okay, so if you have a look at a couple of diagrams down here, you've got chains and you've got rings. Now where we've got a single line between carbon and hydrogen, as we've said, that represents a single covalent bond. Whereas where we have 2 or more lines, you would describe that as a double covalent bond. Which means they share 2 pairs of electrons. Now, remember we mentioned the word saturated, so I'll just change the colour of this for a moment. And saturated means carbon uses all of its available covalent bonds. So therefore, all bonds are being used. Now, where a molecule is saturated and it has a single covalent bond, we've called these already alkanes. Whereas where it has a double covalent bond, has a slightly different name, we call it an alkene. And we will come on more onto alkenes later on in this unit of work. Now, if we've done that bit, what we have to bear in mind is that the way in which carbon and hydrogen atoms are bonded, so whether we have double bonds, whether we have single bonds, and the shapes of the molecules, the bonding determines the shapes, so it can affect the geometry of the molecule. So bonding affects molecular shape, and in turn the bonding and the molecular shape affects the properties of a hydrocarbon. So, in that respect, what do we mean by the term properties? So it's the properties of alkanes. The properties of hydrocarbons are relative to the size of the molecule. The melting points and the boiling points display this trend eloquently. We'll talk about those in a moment, but we're talking about the word properties. Now, properties you might also describe as a synonym of features. So the features of hydrocarbons are relative to the size of the molecule. Now, what that means, in simple terms, if the size changes, the properties change, the features of the hydrocarbon change. So, if we have a little look at the table below, we've got the number of carbon atoms in each of these alkanes. So it might even say these are alkane names. So what we're looking to figure out is the relationship between the number of carbon atoms per molecule and the melting and boiling point. So if you turn over, what I would like you to do now is I'd like you to pause the video, and on the next page you will see some small graph paper. If we just turn over, you see some graph paper like this. What I'd like you to do now is I'd like to plot a line graph of the two bits of data with the number of carbon atoms along the bottom of the axes and the temperature up the side of the axis. If you have a look, there are two sets of data, so you'll be looking for two lines. So I want you to pause the video and I want you to have a go. If you are unsure, you can obviously carry on watching the video and you'll see how to plot the data, and you can plot along as we go. So if you pause the video and you have a go, and if not, carry straight on watching and we'll plot the graph now. So if you're plotting the graph, you need to mark off your axes. Now, you appreciate I'm doing this on an iPad, so I don't actually have a ruler. So please bear in mind my lines won't be as straight as yours because you'll be using a ruler, but you plot your axis down the side here and your axis along the bottom here. Now remember, as we said, along the bottom we are going to have the number of carbon atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Label the axes. Number of carbon atoms. atoms. So remember, this is the number of carbon atoms per molecule. Up the side, we're going to have the temperature in degrees Celsius. Now, you'll see the table covers quite a range. So down the bottom, if we're going to go in equal amounts, we probably want to start about minus 200 degrees. And it goes up to about 200 degrees. So we've got 10 blocks. So if we maybe split it down into blocks of, let's go with 50s. So minus 150, minus 100, minus 50 degrees Celsius, 0 degrees Celsius, 50 degrees Celsius, 100 degrees Celsius, and 150 degrees Celsius. Now, if we pick a separate colour and we plot the points for our melting points. So as you'll see, if we plot the points, if we've got one carbon atom and two, about minus 182 and about minus 183 degrees Celsius. We then move slightly up when you've got 4 carbon atoms. And then we skip across to 7 because that's our next number. And I think we're close to a minus 100. And I think it's about minus 67 maybe. And I think we're getting close to about minus 30 when we hit 10 carbon atoms. Now, we're looking for a rough shape, so start here. And I think we're probably going to go for a straight ruled line of best fit because it's not an obvious curve there, is there? And if we just write on the side melting points, then if we have a look at our boiling points, do the same idea. We plot roughly similar place to begin with. Then the boiling point, increase at a much steeper rate. So when we get to butane, the boiling point is actually 0 degrees Celsius already. Then we jump up close to 100 for heptane, and then plus 100 for octane, and we're nearly at 200 for decane. So again, probably just going to go with a straight line of best fit. Right, boiling points down side. And also, I want you to mark off a line for me about 20 degrees Celsius because we'll use this later. And on this line, can you write room temperature? So, we've plotted the data. Now we need to ask some questions about it. So, if you have a look underneath, there are some questions that we can now interpret using this graph. And the questions themselves, relatively self-explanatory. Describe the relationship between the number of carbon atoms and the boiling point. So what this is asking you is, as the number of carbon atoms increase, what does the boiling point do? So you go from 1 to 10 carbon atoms, that's increased. What has the boiling point done in terms of, has it gone up or has it gone down? And you'll see that the relationship is that the more carbon atoms per molecule, does the boiling point get higher or does it get lower? At 1, it's down as minus 150. At 10, it's up near 200. So more carbon atoms per molecule, the higher the boiling point. And if you have a look at the same relationship for melting points, go from 1 to 10. What happens to melting point? Starts here. Does it get higher or lower? It gets higher. So the relationship is the same. So the more carbon atoms per molecule, the higher the melting point. Now, next question. Name the hydrocarbons that would be gases at room temperature. So as you'll see here, this is our room temperature, about 20 degrees Celsius. Now, if something is a gas, it has passed its boiling point. So what is the name of the 3 hydrocarbons that have already passed their boiling point before they reach room temperature? So it's asking you for the names. So if you look back at the table, you'll see the names. For 1 carbon atom per molecule, it's methane. For 2, it's ethane. And for 3, it's butane. And then turn over to see there's 2 more questions. Name the hydrocarbons that would be liquids at room temperature. So if we're thinking about this, what that means is they have not passed their boiling point. So we're looking at the other ones. We're looking at heptane. We're looking at octane. And we're looking at decane. Now, next question. Predict the melting and boiling point of pentane. Think shapes, if you're never sure with hydrocarbons. How many sides does a pentagon have? It has 5. So therefore what we're saying is pentane has got 5 carbon atoms per molecule. So how are we going to use the graph to predict the boiling point and the melting point of pentane? So let's highlight 5 carbons here. Then, like you might have done in maths, the way in which you do this is you read up. So you read up until you hit the melting point. And simply, you'd read across with a ruler. And your melting point would be about here. So if we were being super accurate, we'd be able to come to that number. So we might say it's about minus 125 degrees Celsius. You do the same thing with the boiling point. You just continue reading up, and then you read across. So in this respect, where it's come out at, it's about 0 degrees Celsius. And that would be our answers. Minus 125 degrees Celsius, 0 degrees Celsius. Good. Now, if you were doing that, obviously, depending on the scale of the graph paper that you'd use and the size of the graph, you might come up with slightly more accurate answers, because that's not the best graph paper to be using, but the answers that would be expected of you would always probably be within a range. Right, let's carry on. So, if we carry on and look at properties again. So as we said earlier, just remind ourselves, properties, another word of features of hydrocarbons. So the properties of hydrocarbons change as they increase in molecular size. As the molecular size increases, they get longer, the viscosity increases. So it becomes thicker. So viscosity is about the thickness of a liquid. So if you think of the difference between water and golden syrup's thicker, isn't it? It takes a longer time to pour out of a jar than water does out of a glass. That's because it's thicker, okay? And the reason why it gets thicker is you've got lots of long-chained hydrocarbons. So long-chain hydrocarbons, and because there's lots of them, a bit like spaghetti, they get all tangled up. So overall, it makes it harder for them to move, and therefore they move slower. The liquid becomes thicker, and they're described as being more viscous. The temperature at which they vaporize increases. So, temperature at which they turn to vapors, gas. So as they get longer, what we're saying is that their boiling point increases. And then the flammability decreases. They're more difficult to ignite. They're harder to combust or harder to burn. Now, if you've got a longer chain, there are more bonds to break, which requires more energy. Now, as it says, you can draw this out in the table below, but I don't think we need to do that here because we've got all of that information on this page here. So we've got another activity to do. So the properties of hydrocarbons are closely related to their ability to be used as a fuel. What do fuels give us? It's energy. Now, during combustion of a hydrocarbon, in the presence of oxygen, carbon dioxide and water are produced as waste, and energy is released out of the chemicals into the surroundings, which makes it an exothermic reaction. Now, use the information below to answer the following questions. So you've got the number of carbon atoms, you've got their names, you've got a measure of their viscosity, so a measure of thickness, and also a flash point temperature. So what we're saying is this is the point where vapours form, where they become gaseous. So, you've had a little go at that, you've got those properties there. Pause the video now and have a go at the questions here and on the next page. Once you've done that, we'll unpause the video and we'll go through them. Right, hopefully you've unpaused the video. So if you look at the question, describe the relationship between the number of carbon atoms and the viscosity. It's the same idea as the previous questions we did. The more carbon atoms per molecule, looking at the table, does the viscosity get higher or lower? It gets higher. The more carbon atoms per molecule, the viscosity increases. Look at the next one. Suggest a reason for your previous answer. So, as they get longer, what happens to the chains? So, longer hydrocarbon chains, they get caught up and get tangled in each other. Which makes it harder to move. Right, describe the relationship between the number of carbon atoms and the flash point. So the more carbon atoms there are, the higher the flash point. Now the reason for that is that there are more bonds between carbon atoms to break. Now this itself requires more energy. Which means the hydrocarbon itself needs to be heated to a higher temperature. Now, evaluate. So evaluate, remember, is give your opinion. Evaluate the features or properties of hydrocarbons on their ability to be a suitable fuel. So this question is asking you, which is better as a fuel, short or long-chained hydrocarbons? Now, the answer would be short-chain hydrocarbons. The reason for this being is that, as we've said, they're more flammable, which means they require less energy to combust and to be ignited. So they need less energy applied to them to combust and release energy themselves. Right, let's finish the main bulk of this lesson by having a little look at the usefulness of hydrocarbons. So, let's go through this final paragraph together. Let's read through it. The hydrocarbons derived from crude oil can be used to make useful materials we see in modern life. Derived, slightly more complicated word. We might describe it as gotten from. So, hydrocarbons gotten from crude oil can be used to make more useful materials that we now see as essential in modern life. A large amount of processing is required to extract and chemically change the hydrocarbons into ones we want or need. Now, processing is obviously what we do to things, and processing itself requires energy. So we're talking about manufacture and things like that. Most modern day materials rely on crude oil and its derivatives, so the things it's made of, either as a raw ingredient as a source of energy in its production. So how do we get energy out of elements of crude oil? Via combustion, via burning them, these fractions of crude oil. Therefore, a high price is placed on oil because of its essentialness. So it costs a lot. We tend to find smaller hydrocarbon molecules useful as fuel. Now, as we've said earlier, that's because there are fewer bonds to break and release energy from. Fewer bonds to break, which means it's easier to burn and release energy. Whereas we tend to find the large molecules provide a good source for materials such as plastics. Now, sometimes you might see that written as feedstock. And that is the raw materials for production of plastic. Now, as well as that, you can also use it to produce things such as solvents, lubricants, detergents, cosmetics, pharmaceuticals, so it can act as a base product for all of these things. Now, we can also change large hydrocarbons into smaller ones by a process called cracking, which we'll come across in a couple of lessons' time. So cracking is turning large hydrocarbons that might be used for plastics and making things into smaller ones that are used for fuel. And this involves heating and the use of a catalyst, which we'll come across in a couple of lessons' time. Now we've gone through the main bit of content. If you turn on to the next page, you'll see that there's an exam question, but hopefully what I'm going to ask you to do is just ignore that for now. And if you are studying higher tier, you'll be looking at and you'll be talking with your teacher about isomers. So that's a separate bit of content for higher tier, but we're not going to worry too much about that now. And so to finish, what I'd like to do is I'd like to finish by pausing the video and having a go at the knowledge and application checks for lesson 2. And once you've done that, you can unpause the video and we'll go through them to finish. Right, good. So hopefully you've unpaused the video. And if we just go through these to finish. So, state the number of bonds in a carbon atom. Hopefully you've got 4. Forces holding molecules together we call intermolecular. And they're often quite weak. That's why substances can boil and turn from a liquid to a gas. Now, how does viscosity change as molecules become smaller? Substances become less viscous. How does flammability change as molecules become larger? They become less flammable. What are the names of the 2 structure types that we use to describe hydrocarbons? We call them their shapes, rings and chains. The 2 uses of hydrocarbons. We said they're used for fuel, and if they're used as a base product for things like plastics, call them feedstock. What's the name of the process for manufacturing fuel from larger hydrocarbons? Called that cracking. Now, based on the intermolecular forces between the various sized hydrocarbons, explain why the smallest ones are gases at room temperature. As we said, that means they have weak intermolecular forces between them. So they're easier to break and therefore allow the substance to boil or evaporate at lower temperatures. Then explain why larger alkanes are more viscous compared to smaller ones. So we have more carbons, the more likely molecules will get entangled. And then finally, suggest which types, small or long, would be useful as fuel. We've said small because they are easier to combust, to get energy out of an exothermic reaction, and it requires less energy to do this. Good, and that's the end of your lesson 2 on